All right, because IMFs are fairly weak, molecular solids have low melting points. It doesn't take much kinetic energy to start breaking these H bonds. Low melting points, and even water. I mean, water melts at 0 degrees C, but if you consider like carbon dioxide or methane, you know, those melt at even lower temperatures because they have weaker forces. So we'll be looking at those forces. And so low melting point, they're soft. They aren't hard like covalent lattices, or brittle, hard and brittle like ionic lattices. They're soft. They're non-conductors. And their solubilities depend, you know. The solubilities follow this rule: like dissolves like. So polar molecules are best dissolved in polar solvents, whereas nonpolar molecules are best dissolved in nonpolar solvents. Polar solvents, the classic example would be water. You know, water is a very polar solvent. And so when we melt ice, we don't completely break the hydrogen bonds. Hydrogen bonds are still there. That's what holds liquid water together, you know. And so, do liquid water molecules weigh anything? They don't really weigh anything. A single water molecule weighs about 18 U. Whereas, let's say I have a dust pile. If you have a dust pile and you blow on the dust pile, the dust will disperse into the room. But if you have a container of water like this and you blow on it, you don't disperse all the water molecules into the room because they're held together by hydrogen bonding interactions. They aren't really held together by gravity. That's it. And so we'll disrupt this. In fact, when we disrupt it, it loses this nice ordered structure. So liquid water is more dense than ice because things can kind of collapse. But the hydrogen bonding interactions aren't optimized like they are in ice. All right, so let's just summarize this here. We have the types of solids, whether they're crystalline or amorphous. Types of solids are being based on the forces that hold the particles together. So we have ionic solids like potassium nitrate, sodium chloride, magnesium oxide. These are going to be high melting points, generally water soluble, except magnesium oxide is not water soluble. The ionic bonds are too strong. They're brittle, and they only conduct when they're molten or dissolved in water. So there's no translational motion. And then after that, ionic I talked about network covalent here, like quartz and diamond. These are very high melting points. These are insoluble. They're hard, and they're not good conductors. Then we have metallic solids that have a wide range of melting points, from very low to very high, depending on the metallic bond. These are insoluble. They're malleable, ductile. Those are two I didn't put on. And they're good electrical conductors. That's something I didn't put on there as well. They're good electrical conductors because of the delocalized electrons. Okay, and then we have molecular solids. Molecular solids are low melting. Now the solubility depends. This says usually more soluble in organic solvents than in water, not necessarily. These are non-conductors. These are non-polar, so these would be more soluble in non-polar solvents, but then we'd have polar ones as well. Non-conductors in the pure state. Okay, so those are some properties of solids. Now what we're going to do is we're going to look at more detailed properties of liquids. And so I'm going to back up here. But both solids and liquids are going to be held together by forces. And actually, let me talk about the forces here first. The intermolecular forces. For liquids, that's all that's holding them together. For solids, we could have bonds. But what are the intermolecular forces? We have the dipole force, which is permanent. We have the induced dipole force, which is temporary, weight. And then we have hydrogen bondings, which are extremely large dipoles. So those are the key ones. In order of strength, induced are the weakest, hydrogen bonds are the strongest. Permanent dipoles fall somewhere between. So we're just going to take a look at some of these here on the PowerPoint. Bromine chloride has a permanent dipole. Chlorine's more electronegative, and so this is a permanent dipole. And so these molecules are going to be held together primarily by dipole-dipole attractions. That is, the negative end of one attracted to the positive end of the other. Same thing here. And so the orange just shows the electrical attraction here. There's also going to be dispersion. That is, these dipoles can fluctuate in size because the electrons aren't static. The electrons are moving around. And so it can either weaken it or strengthen it. So there can be little waves. Those waves are called dispersion. These are instantaneous induced dipoles. These are the only attractions between nonpolar. If we look at nonpolar, it's like the surface of a pool, undisturbed. It's flat, it's uniform. But in one instant of time, there could be a disturbance here, that is more electrons here than down here. That causes an instantaneous dipole. This instantaneous dipole will be like a ripple on the surface of the pool. Eventually, it's going to settle back down to this. But in that moment when there's a ripple here, that's going to impact the adjacent atom here and cause an induced dipole. So this is an instantaneous dipole that's set up, inducing a dipole. And so these dots represent the instantaneous induced dipole attraction. This instantaneous induced dipole attraction does not last very long. It's very fleeting. It's very short. But if you have enough of those are going to hold those atoms together and prevent them from vaporizing into the gaseous state. These are unusually big dipoles that result when hydrogen's bonded to fluorine, oxygen, or nitrogen. We get a very large dipole. And so here's a dipole attraction between two HFs, but since the dipoles are so huge, we call it hydrogen bonding. It's not a bond like a covalent bond or an ionic bond or a metallic bond. It's just a very big IMF. The attraction between water molecules is hydrogen bonding. The attraction between methanol molecules is hydrogen bonding. And the attraction between water and methanol is hydrogen bonding. Same thing, ammonia and methylamine. Nitrogen's bonded to hydrogen. You can see we're going to get hydrogen bonding interactions between and amongst. Okay. So in this particular slide, we can see the impact of this. Methane is nonpolar. Silane, SiH4 is nonpolar. Germane is nonpolar. And tin tetrahydride or stannane is nonpolar. So all these are nonpolar. And what we're plotting it against is the temperature. And so what we see here is this. What we see here is that the temperature, that is the boiling point. Yeah, boiling point. And so we see this is the highest boiling point, this is the lowest boiling point. If this has the highest boiling point, that means it has the strongest attractions. Now the only attraction that, all these are nonpolar, so the only attractions these have are the instantaneous induced dipole. And so the difference here is the size. So for example, methane's small because carbon only has 6 electrons. However, tin has a lot of electrons. Carbon only has 6 electrons, tin has 50 electrons. So this is like the size of a swimming pool. Tin has a much larger pool, so it can generate much larger waves. Much larger waves means much larger instantaneous dipoles, which means stronger instantaneous induced dipole attractions than methane. Therefore, this is the trend here. That trend is repeated. So for example, we'll see it here. As we get more and more electrons, it's a bigger and bigger pool, which can generate bigger waves, making it stronger as far as instantaneous induced dipoles. Same thing here. All right, the difference between the blue line and the black line is this is polar. And so we have permanent dipole here. Permanent dipole stronger than no dipole. And we're comparing molecules of about the same size. So we're comparing about the same size pool. Here and here and here. And the same thing, this is becoming increasingly polar. So the more polar it becomes, the bigger the dipole is. But these two really stand out. These two are way off the trend. These have very high boiling points. And that's because these have unusually big dipoles. And these unusually big dipoles are called hydrogen bonding. And so the trend here is the bigger the molecule, the bigger the wave or the instantaneous dipole. The more polar it is, the stronger the dipole attraction. And then you have these unusually big dipoles here, which are what we call hydrogen bonding interactions. So that's that chart. You don't have to have that chart memorized, but we can see it here. What we're going to do is we're going to compare the pools of the same size. So this is one way to compare pools of the same size is similar molecular mass. Similar molecular mass is about 28. Nitrogen versus carbon monoxide. Nitrogen's nonpolar, carbon monoxide is polar. And so both of these are going to have about the same size pool, so they're going to generate about the same size instantaneous wave. However, this one has a permanent dipole. And so since it has a permanent dipole, we expect it to have a higher boiling point, which it does. This is polar, non-polar, about the same size. Polar is going to have a higher boiling point. All this is showing is the polar is going to have a higher boiling point. Polar has a higher boiling point because we got dipole in addition to dispersion, versus these non-polar only have dispersion. And so it's just showing some data verifying that the strength, all this verifies the strength. Dispersion, weakest, followed by dipole, followed by hydrogen bonding, which would be the strongest. So that's all the data showing here. Now, these forces are going to impact certain properties of liquids. One property is the boiling point. The stronger the intermolecular force, the higher the boiling point. That is, the higher the temperature you need to boil it. And so what is boiling? Well, let's take a look at boiling first. Here. Boiling. Two things that we should recognize about boiling. One is that the temperature, the higher the temperature, the stronger the intermolecular force is. And two, the amount of energy it takes to boil. The amount of energy that it takes to boil is called heat of vaporization. And so the stronger the intermolecular force is, the more energy is going to be required to vaporize it, that is to completely break apart the molecules. And that's called delta H of vaporization, which is endothermic. The reverse process is called condensation, where we take the gas and recondense it into liquid. That's exothermic. And so actually they're kind of equal and opposite. That is, they are equal and opposite. The amount of energy it takes to vaporize is the exact same amount of energy that's released when it condenses. This is why steam burns. To boil water takes a lot of energy. It takes time. This is why I recommended starting the boiling water bath ASAP, because it takes so long to boil it, because the delta H of vaporization is kind of high for water. Well, likewise, steam burns are very dangerous. Steam burns are very dangerous because when steam condenses back to liquid water, it releases a lot of energy. It's quite exothermic. Okay, but what exactly is boiling? Well, in order to better understand boiling, the boiling process, we need to look back a little bit farther at something called vapor pressure. Vapor pressure is, when you generate a water vapor, it generates a pressure from the collisions of the water molecule against the walls of the container. And we have something called equilibrium vapor pressure, which we'll talk about, but let's look at vapor pressure in general here. We could have dry air. Dry air has zero humidity. Dry air, there's no water vapor in here. or we'd have wet air. Wet air is humid air. And how does it get that humidity? How it gets that humidity is that some of the water molecules on the surface, liquid surface, have enough kinetic energy to vaporize off. That's these up arrows here. So we have vaporization occurring. The reverse process is condensation. So we got vaporization and condensation. Sometimes a gaseous water molecule can come down, strike the surface, and get stuck. That's condensation. It strikes the surface and gets stuck, or it can bounce off and stay vapor. And so we have a vaporization. So if we have dry air here, what's going to happen is that dry air is going to become saturated with water vapor because we're going to have vaporization occur here. And so if we start off with dry air, we're going to get just net vaporization. And so we can follow this process using a graph here, like this. And so we start off with dry air, and we have net vaporization occur. But as we build up more and more water molecules, then condensation is a possibility. The more water molecules, the more condensation. The more water molecules in the gaseous state. And so eventually the condensation rate grows. The vaporization rate stays pretty much constant here. Eventually we hit a point where the vaporization rate is the same as the condensation rate. When that happens, we've reached the state of 100% relative humidity. And the air can't get more humid. We've maxed out the air. In other words, we've saturated the air with water vapor. And we start off with dry air, and the air becomes more and more humid until we've hit 100% relative humidity. And then it's just going to stay constant. This is what we call a dynamic equilibrium. An equilibrium means there's no change. And so 100% humidity is 100% humidity at a given temperature. But it's called dynamic because vaporization never stops and condensation never stops. It's just spinning around in circles. So for every 10 water molecules that vaporize, 10 water molecules condense. So there's no net change in the amount of liquid water, and there's no net change in the amount of gaseous water. But this is just going in circles. So dynamic equilibrium, you get it. Now what is 100% relative humidity? 100% relative humidity changes with temperature. It changes with temperature because the amount of vaporization changes with temperature. And so let's take a look at what dictates that. If I have a sample of liquid water at room temperature, not all water molecules have the same energy. This is called a kinetic energy distribution curve. This would be for water at room temperature. And so what this shows is the population. The highest population is here with this energy here. So the bulk of the water molecules have an energy here. But there's a small fraction of water molecules which have very high energy shown here. This E is the threshold energy required to vaporize. So any energy above this E here is enough to escape the surface of the liquid water, go into the gaseous state. And so it's impossible to turn off this because this is at room temperature. And so vaporization never stops. Vaporization is always going to continue. So at room temperature, that's going to generate gaseous water molecules. Those gaseous water molecules are going to generate a pressure. And so the pressure, we call it vapor pressure of water, is the pressure of the collisions, water molecules colliding with this. So there's going to be air and water colliding. Surface, inside surface. Now what happens with temperature? What happens with temperature is we can increase the humidity or we can decrease the humidity. That is, we can increase 100% relative humidity or we can decrease 100% relative humidity. So if we increase the temperature, this magenta is room temperature, this blue is high temperature. If we increase the temperature, the whole distribution shifts to higher energy. So now the bulk of the water molecules have an energy here versus an energy here, so they're just higher in energy. If I look at the fraction of higher energy water molecules, it's a lot bigger, so we're going to get more vaporization. And so at higher temperatures, the humidity climbs up, the 100%, that is the saturated, climbs up. In fact, we can graph this out. If we graph this out, this is what the graph looks like. And so the higher the temperature, the more vaporization we have. And so this is the 100% relative humidity line. Eventually, we'll hit a temperature at which the vapor pressure hits 1 atmosphere, that is 760 millimeters of mercury. When the vapor pressure of water hits 1 atmosphere, then the water will start to boil. If the atmospheric pressure is 1 atmosphere, this is called the normal boiling point, because the normal atmospheric pressure is 1 atmosphere, and if the vapor pressure hits there, then we're there. The normal boiling point. Well, that's the normal boiling point, but if the atmospheric pressure were lower, then water boils at a lower temperature. If the atmospheric pressure were higher, it boils at a higher temperature. And so we have normal boiling point, which is 100 degrees C for water, and then we have boiling point depending on what atmospheric pressure is for that day. It could be lower or higher. Okay, that's water. Water has hydrogen bonding interactions. Ethanol also has hydrogen bonding interactions, but ethanol's vapor pressure is lower because it has weaker intermolecular forces. Water has greater hydrogen bonding interactions than ethanol does. Dialkyl ether only has dipole interactions. So dipole interactions, so that means the vapor pressure is much higher, I should say, not lower, higher for a given temperature. So water has a vapor pressure here, let's say this, at this temperature, where the black line is. Ethanol has a higher vapor pressure here, and dialkyl ether has a much higher. In fact, dialkyl ether vapor pressure hits 1 atmosphere at only 34.6. And therefore, dialkyl ether boils at 34.6, ethanol boils at 78.3, and water boils at 100 degrees C. Here. This is a vapor pressure curve. So when we go back to boiling, what's happening when water boils like this is that the vapor pressure, we've increased this, so the rate of vaporization increases, and then when the vapor pressure equals the atmospheric pressure, we get boiling occur. So the boiling point here, if the atmospheric pressure is 100, excuse me, 1 atmosphere would be 100 degrees C. So that's boiling process. There are other properties of a liquid that are influenced by the intermolecular forces. And so one is vapor pressure. The weaker the intermolecular forces, the higher the vapor pressure. The stronger the intermolecular forces, the lower the vapor pressure. And so water had stronger, dialkyl ether had weaker intermolecular forces. That has to do with vaporization or evaporation. We had heat of vaporization. The stronger the intermolecular forces, the higher the heat of vaporization. We had boiling point. The stronger the intermolecular forces, the higher the boiling point. We also have some other properties as well. Viscosity. Viscosity is the resistance to flow. So for example, maple syrup. Does maple syrup flow easily, or no, it flows real slow. And so maple syrup has high viscosity. The higher the viscosity, the more thick or more viscous things are, so less tendency to flow. And so high viscosity means strong intermolecular forces. And we have something else, surface tension. Surface tension is the energy required to break the surface of the liquid. We'll talk about surface tension here in this slide. It turns out that being a surface molecule isn't the best job for water. Water would much prefer to be an interior bulk molecule. And the reason is because this is going to be lower in energy. This water molecule has lots of hydrogen bonding interactions in 3 dimensions all around it. Whereas this water only has hydrogen bonding interactions below it here. Above it, there's nothing. And so this is going to be weaker. That is higher in energy than a bulk. And so what tends to happen is water tries to minimize the surface area. We could see this minimization of surface area in drops. When we look at the shape of a drop of water, what is the shape of a drop of water? The shape of a drop of water is a sphere. And a sphere is, one property of a sphere is it's got the lowest surface area for its volume. And so we can just demo, I'm going to just demo surface tension here. Let's see. If I have a steel paper clip like this, Does the paperclip sink or float on water? Well, metal should sink or float. It should sink. But if I'm very careful here with the surface, I can get the paperclip to float. And so here the paperclip is floating on water. Why? It should sink. Why? Because in order to break the surface, it's got to create more surface molecules, which is unfavorable compared to interior molecules. So the paperclip is floating on the surface of the water there. You can see that. Okay, so that's surface tension. So the higher or the stronger the intermolecular forces, the greater the surface tension. So for example, is it easier to float a paperclip on maple syrup or water? Maple syrup, maple syrup is going to be harder to break the surface. And so here is a little table showing some of these and the impact of intermolecular forces. So for example, if we have strong intermolecular forces versus weak, the stronger the intermolecular force, the higher the vapor pressure or the lower the vapor pressure. So the stronger the intermolecular force, what's happening to the vapor pressure? It's going down. And so the stronger the intermolecular force, the lower the vapor pressure, meaning it's harder to vaporize. The stronger the intermolecular force, what's happening to the heat of vaporization? It's going up. The stronger the intermolecular force, the higher the heat of vaporization, which means it costs more energy to vaporize. The stronger the intermolecular force, the higher the boiling point. It's going to cost you more temperature. It's going to require a higher temperature to boil. And so these are the kinds of trends you want to just be aware of. So let's take a look at some sample problems. Chapter 15 starts off with mixtures of gases. So we actually did this as part of chapter 14. So we've already gone through these first questions here. And so let's take a look at the homework problems I assigned for chapter 15. So we're going to go to 11, 19, 25. 11, 19, 25. 11. How do intermolecular attractive forces influence the boiling point? So let's just say the stronger the IMF, the higher the boiling point or the lower the boiling point? The higher. So what they said. The stronger the IMFs are, the more motion is needed to separate the particles within the liquid and the higher the boiling point will be. That's 11. Let's go to 19. 19. The level at which a duck floats on water is determined more by the thin oil film that covers its feather than by a body density that is lower than the density of water. The water does not mix with the oil and therefore does not penetrate the feathers. If, however, a few drops of wetting agent are placed in the water near the duck, the poor duck will sink to its neck. State the effect of the wetting agent on surface tension, intermolecular. Have you heard of wetting agents before? Wetting agents are surfactants, like this. Windex is a wetting agent. What Windex does is it lowers the surface tension of water. It disrupts the intermolecular forces, so it's easier to break the surface. Have you seen this magic trick before? The magic trick is this. The paperclip is still floating here. But, if I time this right, I can get the paperclip to drop on my command. You know how I can do that? how I can get the paperclip to drop is I'm going to squirt some Windex on the side of the beaker, and then it's going to drip down to the surface. And when it hits the surface, then it's going to spread out over the surface. And if I time it right, as it spreads out over the surface, I can command the paperclip to drop just at the right moment when the Windex hits the, because the Windex is going to lower the surface tension. So first off, let me spray some Windex on the inside wall of this. And then let it, oh shoot. That didn't work so well. I sprayed a little bit too much. Well, what's supposed to happen is it drips down here and then spreads out, diffuses, and then I can command it to drop. But it dropped too soon because of the Windex. But now this is a cruel trick you can play. You can bet your friend. You know, I can balance I can get a paperclip to float, but you cannot. And that is, after you add the Windex in here, it's impossible to get this thing to float on the surface, no matter how many times I try this. Is it going to float? Let's see. No. And so it's because it's not fair, because the surface, I just changed the surface tension like this. You can also see this now here. I added the Windex to the water, so when I spill the water on the table and spread it out, it spreads out into a thin layer on the table. Versus if I just have water, what happens with water is it pools up into pools. And so you could see the difference. It's hard to see there, but you can see the difference at home. This is going to form a thin film of water. This is going to pool up the water. So you try to spread it out, and it tries to clump up back together. Well, that's because when you clean windows, you want it to spread out over the entire window rather than pool up and bead. And so this is the concept here. That if you put surfactant or wetters, water wetters, it makes water wetter. How can you make water wetter? You can make water wetter by spreading it out. That's how. And so wetting agent reduces the surface tension of water, causing it to spread out more rather than clump up, overcoming its intermolecular attractions and allowing it to penetrate the duck's feathers. The duck's buoyancy is reduced and it sinks. That's 19. 25. Look at that. Other things being equal, which produces stronger intermolecular attractions? Induced dipole or dipole? What's stronger? Induced, that is instantaneous dipoles, or permanent dipoles? Permanent dipoles are stronger, so dipole forces are stronger. Now, what do they mean by other things being equal? What they mean by other things being equal is the size of the pool, you know, because what happens is these induced dipole, let's say you're looking at a permanent dipole in a baby pool, which is this tiny wave, versus an instantaneous dipole in the ocean, which is a tidal wave. You know, in that case, the instantaneous dipole, this tidal wave, is going to be a lot bigger than the little wave in a baby pool, right? Even though the little wave in a baby pool is constantly running. So we have to compare things that are equal in size. And so, take a look at the answer. Other things being equal, dipole forces are stronger than induced dipole forces. Induced dipole forces are likely to be larger than dipole forces when the molecules are very large. And so, yeah, when the molecule grows very big, then those instantaneous dipoles can become very big as well. In fact, instantaneous dipole can be incredibly strong, like this. In 2002, a team of scientists discovered that these instantaneous dipole forces among millions of tiny hairs on gecko feet in the surface are what allow these lizards to adhere to walls and ceilings. So these lizards can climb on walls and ceilings due to instantaneous dipole forces of attraction. So they can be quite strong. 27, 31. What are the principal intermolecular forces in each of the following compounds? So what are the principal intermolecular forces instantaneous dipole, dipole, and H bond. And so let's look at this one. This is called dimethylamine. What is it here? The principal, the most important one. And this one would be H bonds. Nitrogen has a hydrogen. So whenever hydrogen is bonded to a nitrogen, oxygen, or fluorine, that's called H bonding. So diethylamine, H bonds. What about this one? Difluoromethane. Are these hydrogens bonded to fluorine, or the hydrogens bonded to carbon? To carbon. And so CH2F2 would be what? Well, it's going to be tetrahedral. And if I look at the dipole here, two fluorines are pulling this way, so the dipole is going to be pulling this way. And so this is going to be a permanent dipole. You know, delta minus on the fluorine, delta plus on the carbon. And so CH2F2 is going to be dipole. How about C3H8? What is that going to be? Induced, yeah. Induced. So H bonds, dipole, and induced. Let's go to 31. How about methane and ammonia? So what we have to do is we have to predict which one has a higher boiling point. Well, both of these are kind of the same size, you know, the same size, kind of swimming pool type deal. Methane versus ammonia, same size meaning electrons. We're looking at first row, second row, you know, first shell, second shell. Both of these are second shell. So which one should have a higher boiling point, methane or ammonia? Ammonia. Why? Yeah, hydrogen bonding interactions. Methane has no hydrogen bonding interactions. Ammonia has a higher boiling point because it has relatively strong hydrogen bonds between its molecules versus relatively weak induced dipoles between methane molecules.